Welcome to week 12 of the NPTEL course on coherence and quantum entanglement. This is the 12th week, which is the final week for this course, and today will be the final problem solving session for the course. But other than that, we will also have one revision session which will be held tomorrow at 3 p.m. Tomorrow's session will be more like we will just go through the topics that we have seen, maybe see a few questions, and just overall revise what we have learned in the course. And if you have any queries, you could ask then. Okay, so let us get started with this final week. The first problem is on Schmidt decomposition. Prove the existence of Schmidt decomposition. So we need to show that Schmidt decomposition exists. Suppose psi is a pure state of a composite system AB. Then there exists orthonormal states phi A for system A and orthonormal states phi B for system B, such that phi is a superposition of tensor product of phi A phi B with Ci as the coefficients which are non-negative real numbers, such that sum of Ci squared is equal to 1. This is the normalization condition, and these Ci are known as Schmidt coefficients. Find the Schmidt decomposition of this particular state that is given over here. Psi equals HH plus HV plus VH whole divided by root 3, which is the normalization constant, and then obtain the entanglement of formation. So we have seen previously how to find the entanglement of formation in the lectures. We will find it over here for this particular state. Also study the entanglement of formation of the state, this general state of HH and VV with coefficients alpha and beta as a function of alpha. Okay, so go through this question for a few minutes and then I will solve it. Okay, so let us now solve the question. So let us first consider the simpler case where the dimension is same for the systems A and B. And let the dimensionality be n. and their basis vectors are phi A and phi B. Then we have this expression for psi, where dij are the complex coefficients. Now we can use singular value decomposition. And this complex number is the matrix element of matrix D. So we have this matrix D, which can be written as follows, where this D prime is a diagonal matrix. This is the singular value decomposition. And U and V are unitary matrices. So let us now look at psi once again. So D we are replacing with this, and this is the matrix multiplication. Now let us define this phi tilde as the following. For A as well as for system B, and let Ci be equal to Dii. Then our expression for psi reduces to the following. So this is same as saying Ck equals dkk. This index is just a dummy index. sorry, so this is a dummy index. We can just replace k with I, here also j with I, and this is what we get. This is the Schmidt decomposition. And these are orthonormal because u and v are unitary and these original phi A, phi B were taken to be orthonormal. As a result, this phi tilde are also orthonormal. So thus we have proved the existence of Schmidt decomposition. So this is the Schmidt decomposition. At least for the case when the dimensionality of both the systems are same, which is the typical situation that we will find ourselves in when performing experiments. Of course, you can generalize this to situations wherein the dimensionality is not same, but right now we are only looking at the case when the dimensionality is the same for both the systems A and B. So now let us look at the next part of the question, which is to find the entanglement of formation. So let us look at the next part. So psi is given to us as the following. Now the density matrix for this will be written as this. Now let us put in and see. We are just opening up the brackets. Now let us write it in matrix form. Now the order is taken as follows. So this is HH, this is HV, this is VH, and this is VV. And similarly here also it is HH, HV, VH, and VV. So you decide one particular order and then you have to stick to it and be consistent with it. And this is the standard order that is taken. Now we can find the density matrix for the system A by taking trace over system B. And this is coming from here, that if row AB is the following, then this is how it is given. And using that only we have found from here this row AB to row A. So dot product of H with itself is 1, dot product of H with V is 0. So this is 0, this is 0, this is again 1. Yeah, so H with, so you need to look at, wait, this dot products of B1 and B2. This with this survives, H with V is 0, this with this survives. So you have HH plus HV, V with H is 0, V with V survives, that gives another HH, V with H is 0, H with H survives, that gives me VH, then H with V is 0, and H with H survives, which gives me VV. Now in matrix form, this will be written as follows. Again, the ordering here is as follows. This is H and this is V. Same, this is here H and this is here V. Similarly, row B will be trace of A over A for row AB, and this also comes out to be the same. And how, again you can see, let me highlight. This time we are taking trace over system A. So dot product of A1 with A2 we need to see. So A1 with A2, so this survives giving me HH. Then this survives giving me HV. This does not. Then this survives giving me VH over here. HH, HV, VH I have. Then this survives giving me VV. This does not, this does not, this does not, and then this survives giving me another HH over here. So that's how these terms are there. So row A turns out to be same as row B. Now let us look at the eigenvalues. So using the quadratic formula gives us the following values for lambda. Now let us look at lambda 1. And find the eigenvector. Now let me write it in augmented matrix form. And let me perform certain row operations. Now we can find out the vector. So if b equals 1, then a becomes 1 plus root 5 over 2, and thus the eigenvector for eigenvalue lambda 1 is given as follows. And then we can normalize it. Similarly, for the other eigenvalue, the eigenvector is as follows. Thus, we can write the Schmidt decomposed form as follows. This is given by because we have two eigenvalues. Now we can finally find the entanglement of formation. So entanglement of formation is given as follows, where these lambdas are the eigenvalues that we just found out, and also these are the coefficients in the Schmidt decomposition. And this logarithm over here is to the base 2. So this is the following. So let me bring out my calculator and plug in these values. So 3 plus root 5 equals, then divide by 6, enter, then square of that, this equals this. Then we need to take logarithm of this as well, times this. So okay, this, and then add the next term, which is 3 minus root 5 by 6 squared times logarithm of 3 minus root 5 by 6 squared. Okay, I'm just typing it out in my calculator. You also put it in your calculator. Okay, so final answer comes out to be approximately 0.396. So that's the entanglement of formation. Now we need to consider the general state. Consider this state, and obviously alpha squared plus beta squared equals 1 for normalization. Now in this, so this is the Schmidt decomposed form itself. So we can write down the entanglement of formation. This will be the following. And the maximum occurs for alpha equals 1 over root 2, which is equal to beta, and the maximum entanglement of formation comes out to be and this is approximately 0.707. So maximum entanglement of formation would then be minus 1 by 2 log 1 by 2, and then same thing again, so it's going to be simply minus log 1 over 2. So how I got this is basically, so this is minus 1 by alpha is 1 over root 2, so that squared will be 1 by 2, and then you have same value for beta, so this gives you this. So half log half plus half log half, so half plus half makes it 1, so this makes it simply minus log half, and this will be, so log a by b is log a minus log b, and log 1 is 0, so this is log 2, which is to the base 2, so this is equal to 1. So maximum entanglement of formation occurs when alpha equals beta equals 1 over root 2 and the value is 1 as expected. Now just let us look at the plot for this in Mathematica. Plot of this entanglement of formation versus alpha. So plot of E versus alpha, and then you can clearly see in that plot that when alpha equals beta equals 1 over root 2, then maximum value occurs. So let me open up my Mathematica window to plot this. Okay, so here I am in my Mathematica window, and this was the value of the entanglement of formation for the previous part that we saw. The value of that's what I have put in over here. When I said I'm putting in my calculator, it was over here. So 3 plus root 5 by 6 whole squared times log base 2 of this, and all of that I put in, and then we got this value, which is approximately 0.396 when we do rounding to the third decimal place. And this is the plot. This is the plot of psi versus alpha. Okay, let me put the labels. Instead of C, let me call it alpha. And of course, alpha can take the value between 0 and 1. And let me put the labels. I forgot the syntax. Maybe something like this. Wait, something went wrong. How do I put the other label? Oh, it is coming out opposite. Okay, so first let me put alpha, then E. Yeah, so this is that. Now better. So this is the entanglement of formation for the state alpha HH plus beta VV as a function of alpha. And clearly you can see that about roughly here about 0.707, the maximum value occurs, which is equal to 1, and 0.707 is approximately 1 over root 2. This is where 1 over root 2 is, and the maximum value is 1. Let me put the, what's that called, ticks, I think. Yeah, this is what I want, something like this. So let me put the ticks. Yeah, so this is where 1 over root 2 is, and you see the value at this point is 1. Let me also plot maybe a vertical line. How do I plot a vertical line? Okay, maybe I understood how to plot the lines. Let me just try. I just went to Mathematica help. So there is an option called grid lines. Grid lines, let me put the grid lines at 1 over root 2. Let's see if this works. Some error. Okay, this I don't know why the stuff is not working. Yeah, now it is working. See? Okay, so at 1 over root 2, you see the maximum value, which is 1. Now I've drawn the grid lines, and that's where it is showing up. Fine. So that's that for this question. Now we can proceed to the next problem, problem number 2. Okay, so problem 1 is completed. Before we proceed to problem 2, if there is some doubt, please feel free to ask. Okay, so there seems to be no doubt. Okay, someone is asking at y at alpha equals 0 and 1, the plot was showing 0. That's because, so if that's the minimum is at alpha equals 0 and alpha equals 1, and e at this case will be equal to 0 because logarithm of 1 is also 0. And at this minimum, that means it is not entangled, meaning separable state. And as you can see, if you just have H, that is not entangled. Entangled, that's just a product state, and or a separable state. Entanglement would be when you have something like H plus V, then that is non-separable or entangled. So that's why at alpha equals 0 or alpha equals 1, meaning if just H is present or if just VV is present, then that's a product state or a separable state or a not entangled state. Okay, so let us now proceed to problem number 2. Consider the cross-spectral density function as W omega 1 omega 2 equals S omega 1 delta omega 1 minus omega 2. So that means no correlation between the two frequencies or stationary state. Consider the spectral density S omega given as follows. It is a sum of two Gaussian expressions centered at different frequencies omega 01 and omega 02. The above field enters a Mach-Zehnder interferometer. Calculate the intensity and the degree of coherence. So this is the Mach-Zehnder interferometer. The field enters here. Then this is a beam splitter, and these are mirrors, and then this is the second beam splitter, and then the field comes out. So there is this delay in one arm and there is no delay in the other arm. So based as a function of delay, we will see some interference, and we need to find out the intensity and degree of coherence. So take a few minutes to think about this problem and then we will solve. Okay, so let us now solve the problem. So we can write down the cross correlation function. So because of this particular form of W, it depends only on tau. The cross correlation function only depends on tau, which is the time difference t2 minus t1. That is, it is stationary. Now let us put in the expression for S omega. Now these integrals turn out to give the following results, and we will just see how. And let us now see how. This is because we have made the substitution omega prime equals omega minus beta, so d omega prime equals d omega, and let us also call a equals 1 over 2 alpha squared. So omega is omega prime plus beta, and this beta term comes out because it's a constant. And then completing the whole squared for the omega prime term. And this integral gives simply, this is the Gaussian integral, gives root pi over a, and this root pi over a cancels with this root 2 pi alpha squared, because a is 1 over 2 alpha squared, and so this gives finally the following. And using this we have obtained this expression for the cross correlation function. Now let us look at the degree of coherence function. This is the degree of coherence. This is because gamma of 0 is 2. Why 2? Because you put in 0 for tau here, you get this exponential of 0 is 1, and then here also plus 1, 1 plus 1, 2. And gamma tau from this above page we can just copy and write. And then using Euler's expression, now what is mod gamma tau squared? Okay, so actually no, we don't need to find out mod gamma tau squared. So this is the degree of coherence gamma, and argument of this is the following. And this will be tan inverse of imaginary part over real part. So imaginary part is the following. Imaginary part over real part. So what is the imaginary part? Imaginary part is here and here, and of course this exponential coefficient. And over the real part is this, along with the exponential coefficient. So that's the argument. Now we can write down the intensity. This is the intensity at the output of Mach Zehnder. Now this phi k is argument of k1 star k2. That's phi k. Now this, because of stationarity, reduces to the following. Now let us keep k1 equals k2 equals k and let it be real. So this will then give phi k equals 0 because it is real. In such a situation, the intensity becomes the following. That's the intensity. Now we will look at some Mathematica simulations for this intensity profile. Let me open up my Mathematica window. We will just see how this intensity is plotted as a function of tau. Okay, so here I am in my Mathematica window, and these are some values that I have taken for A and B, which is the width for the first and the second Gaussians, Gaussian profiles, and the expression for S omega, the spectral density. So I've taken A equals 5, B equals 60, and omega naught 1 as 90, omega naught 2 as 110, with delta omega as 1. And I am just plotting the spectral density over here as a function of omega. So here you see that at 90, this is at 90, omega naught equals 90. The width is very small, which is 5, and omega naught equals yes, sorry, the width is a delta omega squared. So 5 times delta omega squared. So delta omega is 1. That's why I said 5. Um, yeah, so the expression is for the spectral density is over here. This thing is the expression for the spectral density. This part. So this is the first exponential, and as you can see that the width of this first exponential is a delta omega squared, and width of the second exponential is b delta omega squared, but because I have taken delta omega as 1, so the widths can just be taken as a and b. So a is smaller, b is larger, and omega naught 1 and omega naught 2. So these this is the spectral density S omega versus omega. That's the plot. Now here I have just by arg I means argument of gamma, which was tan inverse of the real part, sorry, tan inverse of the imaginary part over the real part. So that's argument of gamma. This this co that I have written is the degree of coherence function. Actually, this is gamma tau. And you might be getting confused as to why this is looking a different term. This is because what I've done is I have found mod gamma tau squared, and once you find out mod gamma tau squared, then mod gamma is just square root of mod gamma tau squared. That's what is happening over here. So mod gamma tau squared is basically gamma tau star times gamma tau, and you can easily find that out. And mod gamma tau squared will be basically square of the real part of gamma tau plus square of the imaginary part of gamma tau. And real part has cosine terms, imaginary part has sine terms. And if you just open up these brackets, then this is what you get. You get exponential of minus a t delta omega squared plus exponential of minus b tau delta omega squared. Instead of tau, I'm just writing down t over here. And then there is 2 exponential minus of a plus b tau squared delta omega squared by 2 times cosine omega naught 1 minus omega naught 2 tau. So this is this whole thing over here inside this square root is actually mod of gamma tau squared. So this is mod gamma tau squared. So mod gamma tau would then be square root of mod gamma tau squared. I could have just taken gamma tau and done mod of gamma tau using a Mathematica function. ABS or absolute is the Mathematica function for finding out the absolute value, but I have just done it in this different way over here. And then finally, I am plotting the function. Now what I have done is I have taken 2 common outside. So we had intensity as mod k squared, I of 0, and inside that bracket we had 2 plus gamma tau cos argument of gamma. So I have taken that 2 also out. So that's why if you take 2 also out, that leaves you with 1 plus half mod of gamma tau times cosine of argument of gamma. And this I am plotting for tau from this range 0 to 3. And this is what you see, these fringes. Now the other case is I have taken A and B widths as the same. So instead of different widths, same widths now I am taking for A and B. And this is what I am plotting. And this is the spectral density. And this is the intensity. And you can see periodic fringes over here. And this is another case of a different A and B. And here the intensity looks pretty much weird. So this is the most interesting case. We have 3 different widths over here. One is this big exponential envelope, Then we have these fringes, like these 4 or 5 fringes clubbed together. That's one uh, frequency, one width. And then these smallest fringes, that's the third width that we have. Okay, so if you want to see in this only, someone is saying if you want to change the values in this, let's do that. Let me put the labels. This is S omega versus omega, and the last plot is intensity versus tau. Now if I increase this separation, let's say plus 10 for this, minus 10 for this. Okay, let's say plus 5 minus 5, that increases the separation by 10. See this, what did this control? This controlled uh, the these the second width, this width. If I change even further, okay, let me copy this one for comparison. Let me copy paste this one for the sake of comparison. So that will be the comparison aspect. Let's make these plots little bit smaller, at least S omega. So see, the exponential part, that width is same. The second width changes if you change the separation. Let me increase the separation even more. Then the second width will become narrower, even more narrower, as you can see here. See, even narrower, this second width, but this exponential envelope and this width remains the same. Okay, now let me change delta omega. So this is the original. Now if I change delta omega, so this is okay, this is too much. Let's make it 5. See, this exponential part is actually changing now. Delta omega has increased, so this width, this overall exponential width has decreased. When delta omega was 1, this overall exponential width was like this. Now if I reduce this thing from 1 to, let's say, 0.5, you see this becomes even broader. See that? Even more broader than this case. Okay, so let's bring it back to the original. Now if I change A and B, A and B are also there in the product for delta omega, so that is also working as if like changing delta omega. See, same effect as changing, similar effect, because A delta omega squared, that's the term in the width that is coming. So if you change A by some factor and if you change delta omega by the square root of that factor, the effect will be the same. Okay, so that's that. We have checked all by changing all these parameters. And if we just shift it, let's try this one thing. If we just shift this, that's just shifting and it doesn't change anything because it's just shifting. So now we come to the final question of today's lecture. So this is problem number 3. Throughout the course, we have considered the time frequency, position spatial frequency, and angle orbital angular momentum bases on the same footing for interference effects. Let us explicitly see with an example. Consider a spatial interference setup which is mathematically analogous to the previous question. And the angular correlation function is as follows. A q1 q2 is s q1 delta q1 minus q2. Again, no correlation between the two spatial frequencies, so it is stationary. And sq is given as follows. The spectral density, sum of two exponentials centered at different locations q01 and q02 with different widths a and b. Calculate the intensity and degree of coherence. So this question is in analogy with problem number 2. It's the same thing, but in problem number 2 was in time frequency domain, and problem number 3 is the same thing in the position spatial frequency domain. So take about a few minutes to go through this and then we will solve. Okay, so let us now begin solving. So intensity at position rho z will be given as follows. So everything is in analogy with time frequency domain. the cross spectral density is given as follows. And degree of coherence Now, because of this particular form of angular correlation function, the cross spectral density function as a function of rho 1, rho 2, z will actually reduce to w of delta rho, and this is in analogy with the one we had for time. So this cross correlation function is essentially t as a function of t1 and t2, but this becomes as a function of tau only because of this particular form of the cross spectral density function. But let us see that explicitly over here. Now this delta function will integrate and give q1 equal to q2. So what we did is we did integral over q2 using this delta q1 minus q2. So this cancels out. and that's because delta rho we have taken as rho 2 minus rho 1. And so this is essentially as a function of delta rho. Now let us find what this delta rho w delta rho is by plugging in the expression for this SQ from here. Note that there is no square root over here in this because it is a two-dimensional Gaussian. This Q is two-dimensional. It has Qx and Qy components. And because it is two-dimensional, so 1 over square root to the power 2, that removes the square root. N-dimensional would be 1 over square root of the term, width term, to the power n, or d if it's d-dimensional. So that's how it is. For two-dimensional, the square root goes away. Now let us consider the first integral. Oh, I forgot this prefactor. Just writing down the x and y components. And this prefactor a is this term over here. Now let us separate the x and y integrals. And this from the time frequency thing that we did earlier. From here we will just take the results. From the analogy. That's for the x term. This is for the y term. Similarly, we can write for the second integral. The second integral, same thing with q naught 2 and a goes to b. This will give us therefore our W is given as follows. Now this is analogous to temporal. If we see q goes to omega, delta rho goes to tau, and w is gamma. And we had seen what this expression for gamma is. Let me just copy it. This was gamma, and you see the complete analogy. Now degree of coherence. Again, tan inverse of imaginary part over the real part. So therefore the output intensity is the following. Now what this R2 R1 is, I forgot to draw the setup for this spatial interference. Let me draw it right now then. So we have two slits over here, like a Young's double slit. Then the screen. This is the center. This slit separation is 2D. This is Z equals to 0. This is some particular Z. Z equals to R, capital R. And this point we are considering. This distance is X on the screen. And this is R1, this is R2, so that means this time is T1 and this time taken is T2. So we have time taken is distance over speed. Speed is c. Also, let k1 equals k2 equals k, and let it be real. So if it is real, then phi k is 0. And for r much larger than d, we have, so r1 over c is, r1 is this distance, so it is x minus d whole squared plus r squared square root over c. And for r much larger than d, by binomial expansion, this becomes the following. Similarly, r2 over c becomes the following. Therefore, r2 minus r1 over c is the following. This one cancels out. The individual squares cancel out and the cross term survives, giving 2xt plus 2xt, which is 4xt. So this is 2xd over rc. Therefore, the final expression for the intensity at the screen is the following. Which is in analogy with the temporal domain. So this brings us to the end of this lecture, and this was the final week of the course, the final problem solving session, and the assignment problems are complete. I hope you have attempted all the assignment problems and all the quizzes and have watched all these problem solving sessions. If not, you could go to the YouTube channel for this course, where I have uploaded all the previous problem solving sessions for this particular course. I'll put it up in the chat box, the link to that YouTube channel. So go ahead and rewatch the videos before your exam. It will be very beneficial for all of you. And today is officially the last problem solving session, but tomorrow we will have one more session at 3 p.m. once again for revision. So that will be like a revision session. We will just go through some of the topics that we have studied in this particular course, and if you have any more queries, you can feel free to ask. And I hope all of you have enjoyed this course and you have learned some new topics in this particular course. And if there are any further topics, you can always reach out to me via the YouTube channel, or you could post it up in the forum for the course, and the instructor and the other TAs will look into the queries, and we will try to provide you with solutions to the best of our knowledge. So so this brings us to the end of today's session and this course. Thank you everyone. Bye. see you for one last time in tomorrow's session. Yeah, so all of you can leave the Zoom meeting now.